Hello guys, good evening. Can you hear me? Yeah. Yes. So how was your holiday? Good. Yeah. Okay. So last class, I think we were discussing gases rate, right? And we had done about real gas, the graph, compressibility factor, the concept of the fact, the pressure correction factors and volume correction factors we have done, right? Unit of A and B, all these things we have done. Yes. Yeah. Could you tell me, just check your notes and tell me, have we done the concept of barometer? How to find out pressure due to liquids? Have we done that? Just check your notes once quickly. No. Fine. Okay, fine. Let it be. So we are moving towards the end of this chapter. Okay, probably today we'll finish it. Okay. So we are going to start today's lecture with, a different representation of compressibility factor, which we call it as Virial equation of state. Virial equation of state. Okay. What is Virial equation of state? Virial equation of state is actually, it is an expression of compressibility factor. Write down. Write down. It is the expression of Z, that is compressibility factor, in terms of, in power series of 1 by Vm. Vm is the molar volume. In part series of 1 by Vm. It is represented by Z is equals to 1 plus, we'll have a constant over here, 1 plus B by Vm plus C by Vm square plus D by Vm cube and so on. This is Virial equation of state. We are going to find out a very important, result from this equation. First of all, we try to understand what is this B, C, and D we have, and then we'll have very important temperature relation, okay, which is very important. So B, C, D are constant. B is the constant, or we also call it as coefficient. Like suppose B is the second virial coefficient. Similarly, C is the third virial coefficient, and D is the fourth, and so on will go. Okay, B, C, and D we have. Copy this down. No, we don't have the value of this. We'll have a relation. We'll see that. Okay. It's just an expression we have given. First term is 1. So like you can say the first virial coefficient is 1, right? Because the first term itself is 1. Okay. Yeah. So next you see, now this is the expression we have from the real gas equation, because the actual thing is the real gas. Ideal gas is just an hypothetical concept, correct? Ideal gas does not exist. So we have the actual thing is nothing but the real gas equation, that is a van der Waals equation, correct? Now from van der Waals equation, we'll try to derive such relation of compressibility factor. And then we'll compare what is this B, C, and D we have, correct? So let's see first the real gas equation. What is the real gas equation we have? Real gas equation is nothing but the van der Waals equation, which is P plus A by V square into V minus B is equals to RT, and I am taking N is equals to 1 here for 1 mole. Okay. We need to find out Z, right? Z is nothing but it is PVM by RT. So first of all, we'll find out P from this. What is P here? It is RT by V minus B minus A by V square. V is the molar volume here. If you multiply this by PV by RT, means we are multiplying with V by RT both sides. So V by RT, if you multiply, we'll get V by V minus B minus A by V RT. Any doubt in this? Any doubt in this, guys? No? Just to multiply by V by RT, so RT will get cancelled, and this V and V will get cancelled, we'll have V in the denominator here. So V by RT is what? V by RT is nothing but Z, compressibility factor. So this is Z is equals to, this further will write 1 by 1 minus B by V minus A by V RT. Okay. Okay. Now this you see, this term that we have 1 by 1 minus V, B by V. So I'm considering this as X. So look at this here. We have 1 by 1 minus X. X is nothing but B by V. Okay. So this we can write it as 1 plus X square, sorry, 1 plus X square plus X cube and so on. This is the expansion of it. Or if this is in GP, so sum of GP, at infinite thing, then we have this. When we have infinite terms in GP, the sum of GP is nothing but 1 by 1 minus X. You can get it from this. Or you can also consider the expansion of this 1 by 1 minus x is nothing but 1 plus x square plus x square and so on. This formula we are going to use here for this expression. Okay, so the expression of g we'll have here is z is equals to 1 plus b by v plus b square by v square plus b cube by v cube and so on, bracket close. And one more term we have, that is a by v RT, which is we have, correct? Okay, now you see, if I take this 1 by v common here from these two terms, 1 by v here and 1 by v here. So the expression becomes 1 plus 1 by v, I'll take common, b minus a by RT plus b square by v square, b cube, v cube, and so on it goes. Just we are simplifying it. Okay. Now you see we are taking the condition of low pressure, because we know ideal gas, real gas behaves in ideal gas at low pressure and high temperature. So at low pressure, what happens? You see, at low pressure, V will be high, and if V is high, then 1 by V is low, correct? Because pressure and volume are inversely proportional, and 1 by V is low, so 1 by V square is even lower, and 1 by VQ is even lower than all those, right? So all these terms we can neglect at high pressure. 1 by V square, 1 by VQ, all these terms we can neglect at high pressure. Sorry, at low pressure. At low pressure, the expression of Z is equals to 1 plus 1 by V, B minus A by RT, and this term we have neglected. So this is the situation we have. Now for the gas to behave as an ideal gas, right? So for an ideal gas, we know, for an ideal gas, what is the condition? Z value should be what? Z value should be 1, correct? And in this expression, you see, for Z to be 1, this term should be 0. Yes or no? This term should be 0, then only Z will be 1, correct? So for this term to be 0, what we can say, for this to be valid, Z is equals to 1, we can say we must have B minus A by RT is equals to 0. Can we say that? Yes or no? CLR, you can type, guys. Correct. So what is T from this? T is equals to, it is RB by A by RB, sorry. It is A by RB. T is equals to A by RB. No, 1 by V, we won't take 0, because first of all, 1 by V, if you take 0, 1 cannot be 0, right? So numerator, you let it be this 1. V cannot be 0 because V is the volume of the gas, correct? So it cannot be 0. It will be minimal, negligible, you can say, but 0 we cannot say. And if you make this V as 0, then 1 by V becomes infinity. So this condition we are ignoring, hence. We're taking this equals to 0. Right? Okay. So for this 0, T is equals to this we get. And this is the formula of T. Means at this temperature, this gases, this temperature and low pressure, it behaves as an ideal gas. And the temperature at which any real gas starts behaving as an ideal gas is called Boyles temperature. Boyles temperature. I've asked many times this question. Boyle's temperature, it is A by RB, right? It is a temperature, write down, it is a temperature at which real gas behaves as an ideal gas at low pressure. Correct? Done? Temperature at which real gas behaves as an ideal gas at low temperature. Okay. We also, this is Boyle's temperature, we also call it as TB. That also you can write. Boyle's temperature, TB, A by RB. Now you see this. Boyle's temperature, TB is equals to A by RB. Correct. And we know A and B will have different values for different gases. It means it is not constant. R is obviously a constant, but A, B value will be different for different gases. Right? It means the Boyle's temperature will be unique for a given gas. Means it will be a different value for CO2 and will have a different value for N2. Will have a different value for O2. But the pressure must be low. Right? So Boyle's temperature will be different from different gases since AB values are different for different gases. Understood? Any doubt in this? Depends on A and B, hence will be different for different gases. No doubt. Done? Okay. So this is one thing, Boyle's temperature. Okay. Sometimes they also ask you the order of Boyle's temperature for a given gases. So A and B, if you can compare the ratio of A by B, and hence you can compare the Boyle's temperature. Okay. Now the next we need to understand here is write down is the liquefaction of gas. What do you understand by liquefaction? Yes. Conversion to liquid. Yeah. So liquefaction of gas is nothing but the conversion of gas into liquid. Okay. So we need to focus on this. How do we convert gas into liquid? Okay. Now you tell me one thing. If you talk about the intermolecular force, which one has more intermolecular force, gas or liquid? Which one has more intermolecular force, gas or liquid? Liquid, right? So we can say IMF, here we have very weak IMF, and here we'll have weak IMF, right? So obviously liquid has more intermolecular force than gas. So it means what? To convert this gas into liquid, we have to increase the intermolecular force. Yes, right? I have already told you that we have a range of intermolecular force for different states, correct? First we have, suppose, gas intermolecular force is this, and then we have liquid intermolecular force, and then we have solid intermolecular force. Okay, you keep on excuse me, you keep on increasing the intermolecular force, you'll get a point, and beyond this point the gas starts converting into liquid. Further you keep on increasing the intermolecular force, beyond a certain point liquid starts converting into solid. So point is, when we have to convert gas into liquid, we have to increase the intermolecular force, right? Now this we can achieve by increasing the intermolecular force. I hope all of you will agree with me on this, right? We have to increase the intermolecular force. So what we need to do to increase the intermolecular force, first is, if the gaseous particles are close enough, suppose this is the situation, gaseous particles are like this, and another situation is this, then obviously here we'll have less interaction than this. Yes or no? Means if the gaseous particles are close enough, they will have interaction. If they are far away, the interaction will be less. So our objective is to decrease the distance, average distance between the gaseous particle. Correct? And this we can achieve by increasing pressure. Because if you increase the pressure, compression happens and the gaseous molecules comes closer. Correct? Understood this? Pressure we are increasing, volume will decrease, gas contracts, and when gas contracts, the average distance between the gaseous particle will decrease, and hence the interaction increases. So first thing, in order to achieve this, what is the first thing we can do? The first way by we can achieve this particular thing, conversion of gas into liquid, is by increasing pressure. Right? In this just one line you write down, as pressure increases, as pressure increases, volume decreases, volume decreases, contraction takes place, contraction takes place, pressure increases, volume decreases, contraction takes place. The average distance between the gaseous particles decreases. The average distance between the gaseous particle decreases, and hence interaction increases. And hence interaction increases. Okay, this is the first, condition here. The second condition is what? We can also achieve the same by increasing interaction, and we can increase interaction by increasing pressure plus by decreasing temperature. What happens with decrease in temperature? What happens once we decrease the temperature? No, it's not that. See, we know the kinetic energy of gaseous particle is equals to 3 by 2 kT. K is the Boltzmann constant. If you go back, check your notes, you'll get this. Yes, the kinetic energy decreases. That's right. Yeah, so Ruchita, we can also say that less randomness and hence interaction will be more. We can say that. That's fine. But actual thing is what we know, the gaseous particles, their kinetic energy is directly proportional to the temperature. You see this relation. Ke is directly proportional to T. So as you decrease the temperature, the kinetic energy also decreases. right? And when kinetic energy decreases, the gaseous molecules, you see, the gaseous molecules crosses each other with a less velocity, right? Because the kinetic energy is less. So when they crosses each other with a lower velocity, right? So they will have the chance of interaction with each other. Otherwise, if the two object crosses each other with a very high velocity, like this, they will cross, right? So the interaction is less. Interaction is not possible in that case. Okay. So with decrease in kinetic energy, what happens? Decrease in temperature, what happens? Kinetic energy decreases, and hence the interaction increases. Or you can also say randomness. The random motion of the gaseous particles will become less, and hence the interaction could be more, right? So in order to achieve this condition, gas to liquid, we can either increase in pressure or we can decrease in temperature. Logic, everything we have discussed. Understood, all of you? Okay, liquefaction. Now you look at this graph. So this axis is the pressure and this axis is the volume. Okay. All of you draw this graph. Okay. So this is the graph we have for liquefaction of gas, and this is a different temperature, you see. This is the temperature T1, this is the temperature T2, at T3, and so on. Yes. Yes. Curves are isotherm. Yes, isotherms are those graphs which we draw at constant temperature. Right. So constant temperature graphs are called isotherms. Correct. Now you see this. At any temperature, what we do, try to understand this, okay? Yeah, it's a smooth, actually it is not a curve like this. I have drawn this just to make you understand, okay? What we get, we got these points actually, this point, this point, this point, all these points, and when we connect these points, we get a graph like this. Okay, it's not like we have a graph first and then we draw like this. First, we have this only. At a given temperature, what we are doing here, you see, pressure we keep on increasing. We are increasing the pressure continuously, increasing the pressure continuously, and you'll got a point here. And at this point, you'll get the first drop of liquid, where the gas starts converting into liquid. So this side we have gas, here we have liquid plus gas, and this side we have only liquid. Okay, so you keep on increasing the pressure. At this point, the first drop of liquid forms, and then here we have gas plus liquid mixture. And at this point, this all the gas converts into liquid, and we'll get a sharp curve here like this. Okay, and the same thing we have at different temperature. Means at T1 we have this, T2 again we have the same kind of graph we get. T3 also we get the same kind of graph. Okay, but the difference in these three temperature is what? That the width of the graph is decreasing, right? The graph goes like it's a bell-shaped graph, no? It goes like this. So width of the graph is decreasing, correct? So when the width of the graph decreases, it means what? The amount of gas that converts into liquid is also decreasing, correct? As we go from T1 to T2 to T3, the amount of conversion or the liquefaction is less. It means what? The relation of these three temperature is what? T1 is less than T2 is less than T3. Means at three different temperature we have done this. So if T3 is maximum, then only we can have this condition possible. Because we know at higher temperature, the liquefaction becomes difficult, and hence the liquefaction is lesser over here, least with T3 temperature. T3 should be the max among the three. Understood? No doubt? Yeah. Similarly, as you keep on increasing the temperature, you will get a point, right? You will get a point. At that point, or beyond that point, you can say the liquefaction is not possible, right? Because you are increasing temperature continuously. So you will get a point, where the interaction among the gaseous molecules becomes zero because you have increased the temperature so much. Ideally, we should decrease the temperature, but here we are increasing the temperature, right? So you will get a point, a value of temperature where the interaction becomes negligible or zero, and then the liquefaction of gas is not possible. And that point or beyond that point, the gas starts behaving as an ideal gas because there is no interaction. And we know the PV graph of ideal gas is like this only. It goes. If you remember this, we have done these things. Yes or no? Yes. PV graph is this only for ideal gas. And the same nature of graph we get here, you see, at this point. Beyond this point, we get the same graph. Because beyond this point, the interaction is zero, gas behaves as an ideal gas, and hence the liquefaction is not possible at all, right? So this point beyond which the liquefaction of gas is not possible, this we call it as the critical point. All of you write down. This point here, as per the graph we have drawn, this point here is the critical point. Okay. So how do we define a critical point? Write down the definition. Write down the definition. See, both way we can define this. Okay. Like above this point, like beyond this point, the liquefaction is not possible, or above this point, the liquefaction is possible. Both way we can define. Once again, guys. Guys, just 2 minutes, okay? Yeah, so we're talking about critical point, right? So what is critical point? How do we define it? Correct? Write down, it is the condition, it is the condition below which the liquefaction of gas is possible. Condition below which the liquefaction of gas is possible. Okay, we can also define this other way, like condition above which the liquefaction of gas is not possible. Both way we can define. So they ask questions like this also, which statement is right or wrong regarding critical point. Okay, so both way you must understand, both way we can define above which or below which, whatever it comes in the option, accordingly you can write your answer. Okay, this is one thing. Now at critical point, we can define temperature, pressure and volume also. Like temperature is what? Write down critical temperature. Critical temperature. The definition of critical temperature is, write down, it is a temperature, it is a temperature above which, critical temperature, I'll write down here. Critical temperature, it is represented by TC. Okay, write down, it is a temperature above which gas cannot be liquefied gas cannot be liquefied no matter how much pressure is applied. No matter how much pressure is applied. So beyond this point, the liquefaction is not possible, because you have already increased the temperature to such an extent that the gaseous particles are moving randomly with a very high velocity. So interaction is not possible, right? Hence the liquefaction is also not possible, right? So critical temperature definition is this. This also, in other way, we can write the temperature below which the liquefaction of gas is possible by applying pressure. This way also we can define temperature below which, or maximum temperature, you can also write down. It is a maximum temperature below which the liquefaction of gas is possible by applying pressure. Okay, so must keep this in mind. Both way we can define. Which one, Shraddha? The last definition. I have written it. Should I go back? Okay, fine. Yeah, so this is the the definition of this. Similarly, we can also define critical pressure, PC. Write down. It is the minimum pressure required to liquefy a gas at critical temperature. Next is critical volume. Write down. It is a volume at critical temperature and pressure. And critical pressure. Okay, TC, VC, and this. Done. All these parameters are actually defined for 1 mole. Okay, we define it per mole actually. For 1 mole, all these parameters defined. Yeah, done. Okay. Now, so what is the condition of critical point? Condition of critical point. This one is also important. If you look at this graph here that you have drawn, this is the critical point we have. You see, this is the critical point. And at this point, you see this line, I haven't drawn here. It doesn't seem to be parallel to this. But this point, you see this line is almost parallel to this x-axis. It's almost parallel like this. Then it goes, graph goes like this. Okay? Almost parallel to x-axis here. So at this point, this graph is parallel to x-axis. So we can write down the slope of this line here. That is dP by dVm, where Vm is a molar volume, because axis is P and V. If it is x and y, then the slope is what? dy by dx. You know this? Slope of any curve in this axis, x and y, it is dy by dx. Correct? It's nothing but the slope. You have this idea, right? You have done this? No or yes? Okay. So like dy by dx is the slope. So here instead of x we have v, instead of y we have t. Okay. So slope of this curve at critical point is dp by dvm. This slope, since it is parallel, so this is equals to 0. Right. This is the condition of critical point. So the condition of critical point here will be, many times they have asked this question. The first condition we can write dp by dvm equals to 0, and hence we can also write the double derivative of it, d2p by dvm square is also equals to 0. So this is the condition of critical point. Okay. Now, with the help of these conditions, we can actually find out the critical pressure, critical temperature, and critical volume. Okay. So we have to find out PC, VC, and TC, right? When I write PC, VC, and TC, obviously it is for critical, point. We also find out the compressibility factor at critical point. So what is the compressibility factor at critical point? Z is equals to, it is PC VC by RTC. It is PM by PVM by RT only. But since the pressure, temperature, and volume is this, so compressibility factor is this. Okay, at critical point. This is at critical point. So our objective is to find out, first of all, PC, VC, and TC. Once we get this, substitute all these things here, you'll get compressibility factor at critical points. All these things are very important. Many times they've asked this question in the exam. So these things are very important. Okay. Now we are going to see how do we find out this PC, VC, and TC. Correct. Simple one, you see, for n is equals to 1, the real gas equals to what? P plus A by Vm square into Vm minus B is equals to RT. Okay. What we need to find out, always keep this in mind, condition we have to apply. So what is the condition? Condition is dP by dVm. So if I find out the expression of pressure, in terms of Vm and we differentiate it, you will get the expression of dV by dVm. Yes or no? Tell me. Pressure will find out in terms of Vm and then we'll differentiate the pressure, correct? So our the objective is very clear. We need to find out this, and in order to find out this, we'll first write down the expression of pressure. So pressure is equals to what? We'll have RT by Vm minus B minus A by Vm square. Then we'll write down dP by dVm. It is minus of RT by Vm minus B square, right? Plus 2A by Vm cube. Okay. And since the condition is what? dP by dVm is equals to 0, we'll equate this to 0. So we'll get here 2A by Vm cube is equals to RT by Vm minus B square. How many of you understood this? Yeah. This is first equation, first relation. It's not done yet, but yes, the first relation is this. We assume this to be as equation 1. Okay, no doubt. We have this expression, we can again differentiate this. Double differentiation, right? So you see this. When we differentiate this, that is d2p by dvm square. This would be 2RT by Vm minus BQ minus 6A divided by Vm to the power 4, and this will again equate to 0. So we get here 6A by Vm to the power 4 2RT by okay, this is equation number 2. Now, could you solve from equation number 1 and 2? These two equations could you solve and find out the value of Vm from this? Try this once. It's very simple. What happened? So right now you're fixing it.
Yes, I'm fixing it. It is okay. So okay, when otherwise it don't happen, as it is a part.
So you will come again with that.
Yes, it's a part.
So do I need to tell you like this is working fine or not?
Oh.
So you will come for sure, right?
You will keep on going.
So do I need to call you or again I have to mail or something?
Sorry,
You will come.
No, machine is what is.
Okay. Yeah, tell me. What is the value of VM you got? Is it 3 times B? Is it 3 times B, I think? Yeah, Archit, it should be 3B. It should be 3B. Check your calculation, Shraddha. Yeah, so when you solve from 1 and 2, from 1 and 2, you'll get Vm is equals to 3 times B. You see, it depends only on B, and B depends upon the gas. So it is also unique for a given gas, right? It's not same for all the gas. This is nothing but the critical volume, that is Vc is equals to 3B, since we have applied the condition of critical point. So Vc is equals to 3B. Similarly, if this Vc you substitute here, right, here you will get Tc then, correct? And the formula of Tc I'll write down. No need to derive it, just write down the formula. Tc is equals to, you will get 8A divided by 27 RB. This is Tc. 8A by 27 RB. This is Tc. And with the help of these two, yeah, 1 second, Shraddha, I'll go back. You can also find out PC, and PC is equals to A by 27B square. This one. Tell me the value of Z at critical point. What is the value of Z? Yeah, that's right, Madhumati. So Z is equals to PCVC by RTC. Yeah, correct, Anya. Correct, yeah. So when you substitute all the value here, the value of Z you will get 3 by 8. This question they have asked many times in all the exam. The value of Z at critical point. Correct? Must remember this. All this formula also you must remember. Suppose if they ask you to compare critical temperature for given gases, you need to compare A by B, ratio of A by B for those gases. Yeah, understood? Any doubt? Done, all of you? Correct. Now, one more term we have that we call it as reduced equation of state. Write down. See, reduced equation of state we define with respect to reduced temperature, reduced pressure, and reduced volume. Correct. So first of all, what is reduced temperature? TR. Write down, it is a temperature with respect to critical temperature. It is the temperature with respect to critical temperature. So TR is equals to T divided by TC. This is reduced temperature. Similarly, reduced pressure that is that is PR. This equals to PR is equals to P divided by PC, and reduced volume VR is equals to V divided by VC. Okay. So from all these expression, if I find out temperature, T is equals to what? TR into TC. It's very simple. TR into TC. P is PR into PC. And V is VR into VC. Okay. Now we have this thing. Copy down this first. We have real equation, a real van der Waals equation. In the van der Waals equation, we substitute this pressure, volume, and temperature in terms of TC and TR. TC, PC, VC we know already. We have just now got the formula. Substitute the values, the formulas, and you'll get the equation in terms of reduced pressure, reduced volume, and reduced temperature. That is it. Okay. Not much important, but sometimes they ask this question: what is a reduced equation of state? Okay, so you will just write down the final expression that you must remember. Method I told you how to do this and do it easily. So the van der Waals equation that we have, the van der Waals equation is P is equals to, sorry, we'll write down this side. We have P plus A by Vm square into Vm minus B is equals to RT. See, we are taking one more for all these, okay? RT. Now P, Vm and T will substitute in terms of in terms of reduced and critical temperature, volume, pressure. And we'll solve this. So when you solve this, the expression that you get is PR plus 3 by VR square. Vm is what? Vm is 3VR minus 1 is equals to 8 times TR. So this is called the reduced equation of state. This is called reduced equation of state. Okay, copy this down. Done? Yeah. So this is it, okay, for real gas. Now, we have to discuss two more things in this chapter. One is the concept of barometer. And before that, we'll do different types of intermolecular forces. Okay, because from the beginning in this chapter, we were talking about